Okay, so to discuss a minimally connected graph, we obviously have to discuss a connected graph. So let's just recap our understanding of a connected graph. So remember, the whole idea behind a connected graph is that if every pair of vertices in the graph is connected, and a way to describe that every pair of vertices in the graph is connected is that you can get from, the one vertice to every other vertice in the graph by a means of a path or a walk. The reason why we can say walk is, remember, in every UV walk, there exists a UV path. So when I talk about this, I'll often refer to it as a walk, but you know that there exists a path, which is just, the more refined version of a walk without repeated edges and vertices and stuff like that. So for a graph to be connected, let's just do an example here. So we have like this kind of situation. As long as we can reach every single vertice, so if we start off with the red one over here, can we get to this one over here? Yes, we can, by going either in that direction or in that direction. We can also check, from the red one, can we get to the yellow one? Yes, it's directly there. And then from the red one, can we get to the green one? Yes. So that's the whole idea behind a connected graph. Means if you choose a vertice, can you reach every other vertice in the graph by a means of a walk or, a path? If you can, then it's a connected graph. And the whole idea behind that is there is no isolated vertices then. You won't have, like everyone is you can reach everyone through someone else. So everyone's going to get the information and things like that, kind of like a viewpoint. If you like picturing like a community, there is not going to be a situation where half the community knows some information and the other half don't, because there's not a connection between them. So that's one of the concepts that, for a connected graph and why it could be important and things like that. Then you have obviously the idea of a minimally connected graph. And minimally just basically means that it is at its lowest, connection. In other words, the moment you remove an edge from this graph, it becomes disconnected. So that's what they say here. If the removal of any edge from the graph disconnects the graph. So in regards to this example that we did here, it's actually not minimally connected because let's just write forward in again. Let's remove this edge. Can we still get to every other vertice? And we start again with this red one over here. Can we get to that one there? Yes, we can, because, well, it goes, there and there. Can we get to the yellow one? Yes, we can, because we can go like that and like that and like that. And then can we get to the green one? Yes, by just going like that. So this is not a minimally connected graph. And one of the ways that you can tell it's not minimally connected is the fact that there was a cycle in this graph. So this graph had a cycle. And if you have a cycle, obviously you can remove an edge and it can still be connected. And that's an important concept that we're going to look at through this section of this coursework. So a minimally connected graph would be if we take something like this and we don't have a cycle occurring. So there's no alternative way if we remove one of these edges to get to all the other edges. So that's the idea behind the minimally connected graph. And there's something very important that you should be able to notice from this. And that is, if you look at this, and we say, hey, for it to be minimally connected, it can't have cycles. What was the definitions we just covered? We covered a definition that a tree is an acyclic graph. So a tree is a minimally connected graph as well. So there is, that dual definitions that are occurring. However, there will be situations where you can have a tree as a subgraph kind of thing, but it is not going to be a minimally connected graph because the tree is the subgraph and stuff like that. So just take that into account. A minimally connected graph is if you remove any edge from the graph and it disconnects the graph. Okay, and very common idea is trees. Then next up, we are actually going to discuss this piece that I just went through here, where I spoke about the fact that if there is a cycle, it is not minimally connected. Then how do you prove that a graph is minimally connected? Well, you remove edges and see, is it still connected? If it's still connected, then it wasn't minimally connected. If it's disconnected, then you know it's minimally connected. And that's going to open up some avenues for, figuring out, well, firstly, if it is minimally connected. And also, finding a minimally connected subgraph inside of a graph. So you can have, a situation, again, this is going to become very important a little bit later, on is there a subgraph where everything is minimally connected, and how is that going to affect, data retrieval, things like that. We won't go too deep into the data retrieval and stuff. We're just going to look at the, case of finding a minimally connected subgraph within a graph. And that is going to help us in regards to giving you the idea that you can utilize this to find information slightly faster. But again, your second, third, fourth years of your academic careers, you'll go into more depth into, changing those algorithms to work for you, whether you're in computer science or physics or, biology, wherever you're going to go end up. So let's go on to the theorem.
Okay, so we begin with the theorem statement. Let G be a connected graph. So the key word there, it's connected graph, with an edge element of the edge set. So E is an element of the edge set. And E is also a part of a cycle. So we're going to name this cycle. We're going to call it CP. So E is part of this cycle. Then if we remove that edge, which is a part of the cycle, your graph with the edge removed is still connected. And we're going to have to prove this. So let's go about thinking about how we're going to prove this. So what have we learned so far? We've learned that if we remove an edge, we still have all the vertices in the graph. So that's important to know. So now we still have all the vertices in the graph. What else have we learned? We've learned that when we have a connected graph, there exists a UV walk for every vertice of the graph. So you can get a walk from one vertex to the other vertex for every single vertex of the graph. So we need to consider that. Okay. So if you consider that, we're going to have to consider the idea of, okay, we're going to have some walk, and that walk is going to include this E edge. And then we're going to say, okay, let's remove that edge. Is there a way to still, get to the other vertex? The point is, yes, there is, because it's a cycle, we can just go around it. But we're going to look at that. So let's just draw an example so you can visualize what exactly I'm talking about. Okay, so there we have an example, and I've created just one cycle situation happening here just to keep things easy. So there we have a cycle, and our edge is part of the cycle. So now let's do a walk from V1 to V6. So we have V1 to V4, V4 to V5, V5 to V3, V3 to V6. So that's our walk. We have V1, V4, V5, V3, V6. Or if we had to write all the edges in, we could basically, do we want to write all the edges in? No, we don't really. But this piece here is that E. Okay, so we have this situation of, we have that edge appearing in our walk. Now, if you had to just look at the graph itself, you could, if you remove that edge, so if you just went and said, okay, this doesn't exist anymore, you can still get to V6 by just going around. So you just go around it. And that is the idea, and that is the approach that you want to actually discuss in your theorem proof. So we're going to talk about this and be like, well, this E is part of a cycle. So you have this cycle that occurs where you have actually V4, V2, V5, V4. So you have that everything connects to each other. So if we had to take all this E, and that's E, remember, it's just E in the different direction. If we had to take that E, we can get to V5 without going, directly V4 to V5, by just going in the other direction. So we can actually just go V4, V2 to V5. And I think I did this slightly in the wrong way. So yeah, you have, no, still good. We could have said we go V4, V5, V2, V4. Now we're going to take out this piece here, this E, and we can do that by going, well, We can get to V5 by going around to V2 and V4. So either direction is fine. Okay, so we have the idea where, because it's a cycle, we can just go around basically. So how do we write that in general terms? So let's just erase what we have. And we're going to write this proof in general terms. So the first thing we're going to do is say, okay, we are going to have two arbitrary vertices. We can call them u and v, we can call them x and y, it doesn't make a difference. Essentially, what I'm going to do, I'm going to refer to them as x and y, so that when we discuss like our rest of our arbitrary vertices, we can just refer to them as v1s, v2s, and v3s, and etc. Then have very specific x's and y's when we discuss everything else. So we're going to say, let x and y be an element of the vertice set. And it's the element of the vertice set where we actually even remove the edge. Now, yes, we are starting with that graph. So you're saying, listen, x and y are vertices, but the vertices of the vertice set with g minus e. But now note that technically they're also a part of x and y, the vertice set of the g graph by itself. Because when you remove an edge, you're not removing its vertices. Okay? Then x and y is also an element of the vertice set of G. Okay, so we have that. We also know that G is connected. So, and as G is connected, so we know that G is connected, therefore there is a walk from X to Y in G. So all we're doing right now is we're building up to the idea of we want the graph, the G minus E graph, to still be connected, but we need to bring in the definition of connected in a concept that we can use and we can manipulate. So in that regard, it is a walk. We need to find this XY walk in the G minus E graph, which means we have to introduce things to explain this general walk. So we introduce two vertices in the graph where we remove the edge, and we say, hey, those vertices are actually in our original graph. But we're also told that our original graph is connected. And we know by a definition of connected that if it's connected, then there is a walk between those two vertices. Okay. So we have those aspects. Now we think about, okay, we have this XY walk, and it's any arbitrary vertices in those graphs. So, okay, what if E is not in that walk? And it's completely, utterly possible that E is not in that walk. If E is not in that walk, well, congrats. You pretty much have shown that it is also a walk in the graph minus that edge. So let's do that one. It's the easiest one. We say, okay, again, we've selected two arbitrary vertices, x and y, and we say they are in the new graph, the graph where that edge is removed. But we know from what we've said about all our graphs, when we remove an edge, the vertices remain. So we know that these vertices are in our original graph. Then we say, well, we know our original graph is connected, and we know by a definition of connected, it means that there is a walk between these two vertices. Then we start investigating this walk. And we say, okay, if E is not in the XY walk, so if you have that edge, that E edge that we're talking about, if it's not actually in that walk, well, then it's going to be a walk even in the graph where that edge is removed. Right? So that makes sense. It's like, if it's not actually in that walk, that walk is still going to be in the new graph. Then the walk is also a walk in G minus that edge. And then you found a walk from X to Y in the G minus edge graph. Okay, and remember these are arbitrary vertices, so that's just the idea. So it's saying any two vertices, we're referring to any of those two vertices as X and Y, and if any two vertices have this, therefore we have that whole connected situation. Now we say, okay, let's do the hard part. what if G is a part of this walk? I'm going to use a new piece of paper for this. So if E is part of the walk, we're going to name, and let's just call that E equal to V1, V2. So we're just going to essentially take a graph, and previously we had the E, V4, V5. We can relabel our edges. Remember, we can relabel our edges, we can relabel our vertices. So we do it in such a way so that our edge is labeled for vertice 1 and vertice 2. So that's just relabeling it. So it's taking, for example, this situation, V1, V2, V3, V4, V5, V6. If we call this one E, we relabel the vertices, so like that's V1 and that's V2. And then you have V3 and V4, V5, and V6. So we can do that. We can totally relabel the graph. It's no big deal. So that's what we do. We say let E be equal to V1, V2. And we say E is a part of this cycle. And let's go back to the color black. And as a part of CP. In other words, we have V1, then it goes, V1 goes to some VP, it doesn't really make a difference, VP, VP plus 1, etc. to V2. So remember, our cycle doesn't have to be very, very short. Here it is short, so we have V1 and V2, V2 and V4. So what we're doing is we're saying V1, V4, V2. So let me just show you a different example so you can actually see what's happening there. And again, the way that we number this, remember, because we can relabel everything, it can go in ascending order. So let's just do this. So for example, we have a graph like that, and here we have our V1, V2 with our edge. So you can see there is a cycle, right? So now what we're doing is we're saying, okay, we're going to have some P, doesn't really make a difference, but what's going to happen is the way that we relabel it, it's going to increase and then it's going to go back to the V2. So I want to call this V7 and V8. So that's basically what's happening there, where our P is 7. And we're going to go V1, V7, V8 to V2. The dot, dot, dot means that it doesn't necessarily have to go from VP plus 1 to V2, because you could have had a cycle with more edges in, so you could have had something like this. So you would have had your V7, your V8, and your V9. And then your V2. So here is your VP. That's your VP plus 1. It goes on, and then it connects to that V2. Okay, so that's what we're saying. We're generalizing it. So we're saying let edge be V1, V2, and we can do that because we can just relabel the vertices of our graph however we please, and as a part of the cycle CP. Then we're going to have a case of we take V1 to V2. Okay, just a side note here, when we do discuss this and we go, actually it isn't actually a big deal. So as a part of VP, and then we have this CP, and we have V1, VP, VP plus 1, all the way to V2. So we have that cycle shown, and as you've seen by the examples of how it's actually working. So you're just going to remove these examples so we have more space, and we're going to continue. Okay, so now we're going to also discuss how the walk goes, and we're going to assume that the walk includes E. So again, I'm just going to first show you an example. So here we have V1, V2. I just want to create a slightly bigger situation. Okay, so here's just an example of a graph, and I've written the edge in there, and we have our, our VP plus B and VP plus 1, etc. I've kept it short so there's less to write. And we have an X and a Y situation occurring. Now what we're going to do when we write this, we're actually going to give a name to the vertice just before. So the one just before here, we're going to name that one S. And the one just after, we're going to keep up the concept of B being the one that happens after, just to link with the previous theorems and proofs we're doing. We're going to name that one. And we're going to name this one B. Okay, and let's just refer to this as X and Y, just so we can see the difference. So now when we write the original walk that we have, and we have original walk, we start with X, we end with Y. That makes sense, right? We have some vertices. We doesn't necessarily have to lead straight away, but there is going to end up being a situation in that walk. We have S, and then we have V1, V2, and then we have, I should have written this in red, V1, V2, and then we have that B happening, and then something happens and we get to Y. So when I look at this one here, there could have been other vertices here. So we're just pretending that there are other vertices there, but we label the one just before the vertice that is connected to the end vertice of the edge that we're removing, S, and we label the other one afterwards B, and that's just to help us out here because we're going to be replacing that V1, V2 with the roundabout of the cycle. So what we're going to do is we're actually going to replace this with the alternative path, which means we're going to go from V1 to VP plus 1 and continue on. And remember, there could be other vertices there. So we're going to end up taking that V1, V2 and replacing it with V1, VP, VP plus 1, dot, 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 all the way to V2. The roundabout of that cycle. So let's write that in general terms. So we say we have a walk. We don't have to say now, we can literally just say we have a walk. We have a walk X dot 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 to S. So it could be XS, but it could be X and some other vertices all the way till we get to that point. And we're just going to write it as V1, V2 like that. So you remember that that's the one that's the edge that we want to remove, the edge that is a part of the cycle. B all the way to Y in the original graph G. Okay, now that is the original graph G because the original graph had the edge in. Now we're going to look at it in terms of, we're going to go around that edge. So we're going to, again, replace that edge with the roundabout walk that goes around it because it's a cycle. Now we replace E with the walk V1, VP, VP plus 1, dot, 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 dot to V2, which gives us a walk as follows, where we have X, S, V1, VP, VP plus 1, dot, 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 V2, B, dot, 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 Y. And now we have this walk that goes from X to Y, but does not contain E. And hence it is a walk in the new subset, G minus that edge. Subgraph, not subset, subgraph, G minus E. So let's just finish off writing that down. And this walk will not contain edge E, and therefore is a walk in G minus E. Okay, so to recap, we say, okay, what if E is a part of the walk? So we start off there. That says part, just by the way, it's an A and an R. And then we say, okay, let's name the edge. And we're going to name the edge V1, V2. and it's a part of the cycle P. And then what we do is we have a cycle, and what we're going to do is when we describe the cycle, we're going to describe it going in the direction that doesn't include that V1, V2. And we do that so that we can automatically shove it in where that V1, V2 is. So it's just that alternative direction. So instead of going direct over here, so we're sitting over there, instead of going direct, we go around. So that's how we name the cycle. So we name it the alternative way around. Okay, then we describe our walk, which has that E edge. So we describe it where it has that E edge, and we just name the vertices before and after, just so that you can get clarity of where it sits. And then what we do is we replace that V1, V2 edge with the cycle that we've just described that goes around it. And because we can do that, we have a walk which will be in the graph that does not have that edge. And then we're done. We have shown that basically there is a walk in the graph where the edge is removed, and because there's a walk and it's all the x's and y's, which are, you know, arbitrary elements and stuff, it is going to be a connected graph still. And that's it. So we are done.